Hello everyone. Okay, so today, as you know, that we are working on the a converging nozzle, and the nozzle name, the test case is the asymmetric subsonic jet. In short, it's ASJ, and it is the from the NASA's turbulence modeling resources. And the nozzle is subsonic means that the flow exiting from the nozzle outlet is having Mach number 0.51. That's less than 1. So we solve the case, and now what we want is that we want to compare our data. So I have compared the data of the velocity on the center line, that is here, okay, over here. So at the end of the nozzle to the outlet, okay. So how much it is, like up to x by d is equal to 20. Now when you talk about the x by d is 20, it means that there are two terms here. Number one is the x by dj or y by dz, and one is the u upon uj, and also we have the velocity in the y direction, and then we have the turbulence stresses, okay. That all can be compared, and also we have the turbulent kinetic energy and other things here, okay. So we have compared the first case that I will show you, and now I am trying to compare the second case, and especially the procedure will be remain same. So if I do for the one case, then you can do it for the remaining cases. So the first case is the s at the x by d is equal to 2, okay. X by dz is equal to 2, and the dz is equal to the 2 inches, because the radius of the nozzle at the exit, okay, we are talking about nozzle at the exit. So inlet diameter is I believe it is 8.5 inches, and at the outlet this is equal to 2 inches diameter, okay. So because we are solving this case as a symmetric, so what we are doing is that we are only modeling the half nozzle, and we are defining this as the axis, and definitely we have defined the outer profile also and the free stream domain, because the flow will be exiting to free stream, and that's how nozzle works. So we have to model the free stream domain as well, that I did already, and you have seen that thing in the slides also in the previous videos. So what we are doing is that we will go to the x by d is equal to 2. So the d is equal to 2, so it means that the x would be equal to 4, but that is after the nozzle exit. So now the location of nozzle exit here is equal to the starting point, like there is straight part on the two sides, so including the straight part here and here as well. So this we started from the nozzle at the x is equal to 0 here, and on this location the x is equal to minus 605, something like that, and here it is 6.85. Let me show you, okay, let me show you. So here 6.825.25, and on the back side it is 0.665, okay. So this value is 6.825, and on this location it is 6.825 plus 0.25, and on the back side is 0.665, okay. So if I add these values, 6.825 plus 0.25, this is equal to 0.7075. 0.7075. Okay, this point. Okay, now where we have to be taking our values, so that is after the nozzle, so that will be distance will be the 4. So in the dimensional numbers, this is like after nozzle exit, but because already we have the x is 0.0 7.075. So this will be the 7.075 plus 4. Okay, and that is equal to whatever distance it is. So we are going to be getting the line at that location. Okay, so here if you like let me show you. Okay, 6.825 plus 0.25 plus 4, this will be the 11.075. Okay. Okay, let's open the Fluent, which is already open on my computer. So I will go for the line. Okay, so the results, create, and this is going to be the line or rack. You can go for the rack also, but I prefer the line. Okay, so this will be at the x is equal to 11.075 and 11.075, and the y location we have to decide. So the y location is going to be the y is equal to the y upon dz. Okay, so it means it's going up to the 1.5, so multiply with the 2, this will be the absolute y will be 3. So here I'm going with the y is equal to 3 and 0 to the 3. Okay, so click on okay, this is in the actually in the inches. Okay, so let me change my units to the inches. Okay, so this is going to be the 11.075. and the y would be equal to the 3. Okay, click on create. Okay, let's check the that line. Okay, so we have the line over here. Okay, let's change the color of the line as well. So it is going to be the a surface. So let's make it black and click on display. This is line over here. Okay, so when we will compare the data, definitely we have to because the line that is by like they are comparing, they have changed their origin to the 000. Okay, so I will be subtracting the 7.075 from the location, and then I will non-dimensionalize. Okay, so we will do it. Okay, so here the catch is that now we have to like plot the data. So the results and xy plot, and this should be along the y-axis, and it is going to be the velocity. Okay, which velocity it is? It is the x velocity. Okay, so the x velocity, so that is the axial velocity here, and on the line number 20, line number 12. Okay, 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 it is. Okay, so if you take a look here, the maximum value we are getting there is u upon uz. So uz is equal to the like as a maximum velocity that we are getting for the jet, and that is at the like if you draw the line. Okay, make the line. So we can take the average value of that over there. Okay, so nozzle outlet. Okay, this is exactly at the 7.705 7075 7 point okay 7.075 7.075 and the second location, because one is exactly the 0 in the y direction, second point has the value of around like a 1, so let's make it 0.99996. okay, so 0.9996 0 and click on create. Okay, now I want to get the this is exactly equal to what? This is exactly equal to the u upon uj. This is the absolute velocity magnitude. Okay, so that does not contain any components. So I will go to the reports, and this is going to be the surface integral. Okay, and I will take the vortex average. Okay, what value? The absolute velocity. Okay, no components, and that is going to be where that is the line nozzle outlet. Okay, this one. Okay, click on compute. This is showing us the value of the jet velocity equal to average velocity equal to the 159.15386. okay, so this is a value that we can use to get the non-dimensional values here. Okay, and you can see that the values are up to the 1. It means that they are taking the maximum velocity. Okay, so if I take the vortex maximum, this value is a 171.818. So I suggest that because the it is starting from the center line where the velocity will be maximum, so its value is coming out to be equal to the 1. So it means that this value should be the maximum value. Okay, so let's do it. Okay, so 171 is with us, and now I'm going to be going back to the XY plot. And okay, write it down, and order points is important because this will make them in a sequence. Okay, so otherwise the random points can be generated, but here the y direction will be from the 0 to the last point. Okay, the last value. Okay, so write it down. Okay, this is this is the 3 cases. We have compared the data in the turbulent pipe flow, 9 degrees band. They are again very nice workshops, and they contain the validation with the accelerated data, with the empirical data, and many things are there. Okay, so go to the our case, and what we are going to put here is that this is the y velocity. Okay, this is the this is the u velocity versus the y. Okay, so click on OK. Okay, now I will be opening this one in the Excel. Already I have got the data from the NASA, and this data was is given here. You just need to click on the this link, axisymmetric subsonic jet data of interest accessed along the line shown in the figure above. Okay, so I'm talking about the x by dj is equal to 2. So the x is equal to it's a constant, which is this is it's a constant which is equal to the 2. So this will be in the dimensional quantity will be 4 after the nozzle. Okay, so we are interested in the y coordinate, and we are interested for the u upon uj, this value. Okay, so from here I have taken the 2 columns only, the first, second column and third column, and this is already in the Excel sheet over here. Okay, so this should be plotted the y-axis should be along the vertical axis, and the velocity should be along the horizontal axis, which is already I did it over here. Okay, same thing I already did here. So you can like change the graph properties, and then I will be importing the data from the our case. Okay. So the numbers like having the 2 are enough, okay, or maybe 1, and same goes here. Okay. So chart title, we can decide what is going to be the title of the chart. So not very difficult thing. Okay. So here, okay. And the second case is going to be our CFD. Okay. So the first thing is the velocity, that is the u upon capital Uj. Okay. And this one is the y upon dj. Okay. That the diameter of the jet, that is the nozzle exit. Okay. So now we have the two values here, and our title would be the velocity at the x by d is equal to 2 along the y direction. Okay, this is the x velocity. Okay. Okay, so you can do decide about the titles also. So let's make it like in this way. Okay. Okay, now we are going to import the CFD data into the Excel sheet here. This is like you can say it is the data from NASA. Okay, this is the experimental data. Okay, this is going to be the CFD. Okay, now import the file anywhere in the sheet. So data, and from text file, and you have to like select all the files, and u velocity versus the y. Okay. So next and finish. Okay, I can get the maximum velocity. Already I have the maximum velocity that I can use here, and that's equal to the 171.818. Okay. So this is here, and you can check it also. So this is equal to the definitely this is going to be on the center line, and but I don't see it. Okay. So the maximum velocity I'm able to see here is the 171.549, this one. Okay. So I think we should use that local velocity instead of the velocity at the nozzle exit. Okay. Okay. So this is from the like vertex maximum. I don't know how they were calculating the values, but here I'm getting the value of the 171.55, which is 549. But here it was like 171.81. So I will be using this value because this will give me the value maximum value equal to the 1. Okay. Now issue is this is like this should like velocity should be on the x-axis. And secondly, we should like okay, let's format the number here, and velocity should be equal to the value of the like y coordinate should be like divided by the 2, definitely first thing, but before that we have to change it into the inches. Okay. And you can see that I have searched on the Google, and change from meter to inches is like 1 meter is equal to 39.370. So that's what I'm going to be doing here. Okay. So put the value here. So multiply the second column by the 39.3701. Okay, and apply on all the values in the same column. Okay. Okay, now you have to copy the values like this and paste here like this. Again copy, because now we pasted as a number. This is not having any reference with the previous column. So now we can directly paste them here and they will be, new values will be now updated here. Okay, this is a non-dimensional value. One thing more that we have to do is that we have to divide this value by the 2. So that is the, now this will become the y by dj. Okay. So again, you can apply them on all the columns, all values in the column. So here we are, copy and paste. Okay. Again copy and paste over here. Okay. Now you can right click on the chart and click on select data, and this is going to be the our CFD. This is the CFD. This is the present CFD, and we have used the essay model. So I will put the name as essay. Okay. Okay, so the formatting should be done. So I think that we can do very easily. Okay, so just let me complete the chart. Okay, sorry, I think I did some mistake. No, I didn't do any mistake yet. Okay, so maximum velocity is equal to the 171.55. So we have to divide that velocity also with the maximum velocity. So 171.55. Okay, same procedure. Okay, now you can bring the chart on the right side and delete all the columns here. Okay, except the one column that will be the gap between the both data set, and also I'm going to leave the only 2 rows on the top side. Okay. Okay, this is the present CFD and with the essay model. Okay. Okay, so you can see that the data is matching very well, and if you take a look on the other chart, that is for the center line velocity, that like a convergence is being shown here. This is the computational setup, the mesh, the geometry creation process. All videos are like you have already those videos, and if you want the videos again, or anybody who is not enrolled into the course, if they want the videos and these files, they are most welcome. Okay, so you can register by the link given in the description, and you will get everything in the Google Drive zip file, single file, which contains the PPT slides in the PDF format, the solved answers files, and also the video recordings. Okay, So this is the first chart that is along the like a center line that is shown here, this one. Second chart is here. So we compare our data and this is matching very well with the CFD data from the NASA. Okay. Thank you very much.